Hi there. For this video, we'll be discussing the rational root test or the rational root theorem. So let's write that one down. Rational root test. So basically, this test is a useful test in determining all possible rational roots of a higher order polynomial equation. So this time we'll deal with equations with a degree of, say, 3 or degree of 5, degree of 8, and so on. So for the rational root test, we have all possible rational roots of any polynomial equations is of the form, this is the important part, it is of the form positive negative P over Q, wherein P is a factor of the constant and Q is a factor of the leading coefficient. So let's dissect this test or theorem further to understand it much better. So first, note that since it's written here that it's only the possible, that means that upon applying the rational root test, all of the outcome that we will get here is still not all the rational roots. It's only a possibility. So we'll still use this to obtain the actual rational roots of the polynomial equation. Next, since it's written here that this is a rational, so by rational roots we mean rational numbers, or numbers that can be expressed as a over b, wherein a and b are integers, such as fractions like 1/2, 3/4, and so on. Then, note that it is written here that this can actually be used in any polynomial equations. So we can actually use this as well in linear and quadratic equations, but we won't really be needing this on those types of equations since using the previous methods that we have discussed is much easier. Now note that for this one, the constant and the leading coefficient here represents this. So let's say this general polynomial, if we have an times x raised to n plus an minus 1 times x raised to n minus 1, and so on up until a raised to 1x plus a raised to 0 equals 0. Let's erase this one with color red. So this one out here is the leading coefficient. So we determine the factors of this to obtain in Q. And for a sub 0, this is the constant since it doesn't have any variable with it. So we use this to determine the P. So take note of this one since I'll probably erase this already to move on with the examples. So let's have our first example. Let's have x raised to 4 minus 3x squared minus 4 equals 0. Since we have a higher degree out here, so this is greater than 2, we'll try to apply the rational root test. So by rational root test, we first inspect the leading coefficient. In this case, it's 1. And then we inspect the constant, which is 4. We can consider negative 4, but it wouldn't really change a thing. Then we list out their factors. So 1, its only possible factor is 1. Then for 4, its possible factors are 1, 2, and 4. Note that we'll only consider positive here since our form is given by positive negative p over q. So it will still cover all the negatives. So again, this 1 out here represents the q, and this one represents the p, which is this. So our possible rational roots are, we can have positive negative 1 over 1 by using this 2. Then we can also have positive negative 2 over 1. And then lastly, we can have positive negative 4 over 1. Or simply positive negative 1, positive negative 2, and positive negative 4. Now, are these the roots of this polynomial equation? Not yet, since again, these are only the possible rational roots. So how do we determine which among these are the actual roots of this polynomial equation? Well, we can apply the remainder and the factor theorem. So by the remainder theorem, we can let this expression out here to be f of x. We'll have f of x equals x raised to 4 minus 3x squared minus 4. What we do is we substitute each one of these out here, and if the outcome is 0 upon substitution, then we can conclude that that certain number is a actual rational root of this polynomial equation. So we'll do that one. So let's move this out here, and let's have this out here. So first, let's try f of negative 1. So at f of negative 1, we'll have negative 1 raised to 4 minus 3 times negative 1 squared minus 4. This is equal to 1 minus 3 minus 4, which is equal to negative 7. It's not equal to 0. Therefore, negative 1 is not a root. How about for f of 1? We'll have here 1 raised to 4 minus 3 times 1 squared minus 4, and this also becomes 1 minus 3 minus 4, which is equal to negative, it should be negative 6, which is also not equal to 0. So 1 is also not a root. So we cross this one. How about 2 and negative 2? Let's have f of negative 2. Upon applying negative f of negative 2, we'll have here negative 2 raised to 4 minus 3 times negative 2 squared minus 4. And this one is equal to negative 2 raised to 4 is 16 minus negative 2 squared is 4 times 3, that is 12 minus 4. And 16 minus 12 minus 4 is equal to 0. Therefore, negative 2 is a root. How about f of 2? For f of 2, we've got 2 raised to 4 minus 3 times 2 squared minus 4. This also simplifies to 16 minus 12 minus 4, which is equal to 0 as well. Therefore, 2 is a root. So now that these 2 are a root. For f of negative 4 and f of 4, you can verify that this 2 is equal to 204, which are clearly not equal to 0. Thus, 4 and negative 4 are not a root. Therefore, we can conclude that the rational roots of the given polynomial equation are positive and negative 2. And that's the answer. So that is how we apply the rational root test. Let's try out this next example. Let's have 2y raised to 4 plus y cubed minus 19y squared minus 9y plus 9 equals 0. Again, we first check the leading coefficient and the constant. So for the leading coefficient, only possible factors are 1. For 9, the possible factors are, it should be this. So the possible factors of the leading coefficient are 1 and 2. For 9, we've got 1, 3, and 9. Therefore, this out here represents the this one out here represents the P, and this one out here represents the Q. So the possible rational roots are positive, negative. We first have 1 over 1. So that will be 1. Then we also have got 1 and 2. So that is positive, negative 1/2. Then we've got 3 over 1. So that's 3. Positive, negative 3 over 2. Next, we've got positive, negative 9 over 1. So that is 9. And lastly, we have positive, negative 9 over 2. And that is 9 over 2. Now, these are our possible rational roots. since the process of solving this one is very time consuming, it's very long, so I'll leave as an exercise. You can verify that the rational roots for this polynomial equation are -1, 1/2, and +(-3). Let's have this final example. Let's have 4z6 plus 8z5 minus 17z4 minus 42z³ minus 16z squared plus 10z plus 5 equals 0. Checking out the leading coefficient and the constant, we know that the factors of 4 are 1, 2, and 4. For 5, that is simply 1 and 5. So again, the constant represents, the factors of the constant represents the p, or the numerator. The factors of the leading coefficient represents the q, or the denominator. So we got here the possible rational roots are given by positive negative 1/1, so that is 1, then positive negative 1/2, so that's 1/2, then positive negative 1/4, so that is 1/4. Then we've also got positive negative 5/1, or that is 5, positive negative 5/2, that is 5/2, and positive negative 5/4, or 5/4. So these are the possible rational roots. And again, as an exercise, you can verify that the rational roots are -1 and positive negative 1/2. And so that is how we use the rational root test. As you can observe, this method is very time consuming. That is why I only leave the application of the remainder and the factor theorem as an exercise, since it would take us forever to do it or to solve it. That is why in the next video, we'll probably try to solve this again, but on that video, we'll try to apply factoring methods and synthetic division. So we'll use those two concepts to minimize the time in solving for the roots of this equation. And also, if you can observe, we only deal with the rational roots. How about for irrational roots, such as radicals like square root of 2, square root of 5, and so on? Note that these irrational are still real numbers, so we still consider them as a root in the real number system. That is why the rational root test is a great method, but it doesn't end there. So we'll dive more into this in the next video. So I hope you enjoyed this one. Feel free to comment down below your answers and solutions to the exercises in this one. So that's it, and that is all for this video.